This rule only works when all the paths are identical. What about when they're not? When they're not, I have to be tricky. Suppose that along this wall, I had a whole bunch of drawers. And in the first drawer, I just had 1 ohm resistors. And the second drawer just had 2 ohm resistors. And the third drawer, 3 ohm resistors, all the way up to infinity. And I wanted to make this circuit. But I could only open 1 drawer. And let's say that I had to make that circuit by adding identical resistors in parallel. They all have to be the same. Now, once you open a drawer, you can take as many as you want, as many as you need out of the drawer, but you can only open 1 drawer, and you've got to make that. Which drawer do you open? Talk to your neighbor. Talk to your neighbor. Which drawer do you open? Okay. Brave soul, raise your hand. Which drawer are you going to open? Where are you, brave soul? The 30 ohm drawer. That's exactly right. And why did you choose the 30 ohm drawer?
Because you split them evenly. I get how I.
Okay.
6 times 5 is 30.
The lowest common denominator is the way we say that in math talk.
Yeah.
Okay. In other words, I can make a 5 out of 30s. I can make a 6 out of 30s. How many 30s would it take to make a 6? 5, right? Because 5 paths are 5 times easier than 1 path. So this would look like the resistance of 1 path, that's 30 ohms, divided by the number of paths, that looks like a 6 ohm resistor. If I wanted to make a 5 ohm resistor, how many 30s would I take out of the drawer? 6. Because 6 paths are 6 times easier, and that, if I take 30 ohms and divide by 6, I get 5 ohms. Now, if I take the 5 and I put it next to the 6, what that looks like is 1, 2, 3, 4, 5. That's my 6 ohm. 1, 2, 3, 4, 5, 6. That's my 5 ohm. And each of these is 30. Now I can calculate the resistance using that rule that only worked for identical paths. The resistance equivalent would be the resistance of 1 path divided by the number of paths. I've got 5 plus 6 is 11. And that's going to give me 2.9 ohms. Now I want you to notice that 2.9 is less than 5. And that will always, every stinking time be the case. When you have parallel paths, the equivalent resistance is going to be less than the least. Less than the least resistant path. Because let's look at it from Fred's point of view. If Fred wants to get through this, Fred could just go through the 5. Right? And be back to the battery. He could just go through the 5. Or, there's another opportunity for flow. There's another door open. That reduces the resistance from the 1 path, the lowest path. Now, If you had gone to Stanford and taken this class, they would have derived a formula that looked like this. If you have two resistors, R1 in parallel with R2, 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. How many of you were taught that in a science class somewhere? Raise your hand. Do you remember where that came from? Neither do I. Neither do I. Okay? I could derive it if I needed to, but I don't need to. Because if my R1 is 5 and my R2 is 6, then this is going to be 1 over 5 plus 1 over 6. When I'm adding fractions, what's the first thing I do? Lowest common multiple. Lowest common denominator, is that what we call it? I try not to hang out in the math department. Frankly, I just don't want their geekiness to wear off on me. Don't tell them I said so. Man. So the lowest common denominator here is 30. So this is the same as 6 over 30. This is the same as 5 over 30. And when I add that, now I can add that. That's 11 over 30. But that's 1 over the equivalent resistance. That means the equivalent resistance is going to be 30 ohms, the resistance of one path, divided by the number of paths, 11. Isn't that beautiful? Suddenly you see where that silly equation comes from. You're replacing the 5 and the 6 by a whole bunch of resistors in parallel that are the same, because you have a rule for resistors that are the same. 6 paths is 6 times easier than 1 path. 20 paths is 20 times easier than 1 path, if they're the same. Check that your neighbor's on the bus, people.